Hello and welcome to this short video on taking control of your part thicknesses in rotational moulding. My name's Gareth McDowell. It's very important in rotational moulding to make sure that you get the right wall thickness of your part. Variation in this wall thickness can have a massive effect on the strength and ultimately the integrity of your part. Simple beam theory will show how a small change in the wall thickness can have a massive impact on the stiffness of your part. Variation in wall thickness will also have an impact on the rate of cooling of the part and thus the crystallinity and effectively, potentially, the level of warpage that you will experience. So in order to minimize these deflections, in order to minimize this warpage, it's important to ensure that you've got a well-distributed wall thickness of your part. Here we have a graph showing the variation in wall thickness of a moulding. This moulding had various internal and external radii. Ribs, external and internal as well. And along the horizontal axis of the graph, at points marked A to Z, we can see the thickness variation from the average designed thickness of the part. And we can see this varies from almost 0% variation, i.e. the design thickness, all the way up to minus 20% and plus 30% of the designed thickness variation of the wall. This, unfortunately, in rotational moulding is a standard variation that one would expect to see. It is not unusual within our industry to see wall thickness variations of up to plus and minus 20%. This is an awful lot more than what we would often expect, but following a call to the industry, this was the number that kept repeatedly coming back to us, plus and minus 20% wall thickness. What this means is if you have a part that has been designed for mechanical strength, let's say at 10 millimeters thick, it is quite acceptable to have parts of that moulding as high as 12 and parts of that moulding as low as 8 millimeters. And that, I would say, is conservative in many parts within the industry. So if we ask the simple question, how does thickness affect the stiffness of your part? We can look at it in a very simple fashion using simple beam theory. So a beam supported at either end with a force or a weight put in the center will deflect. And we can see that the deflection delta, as we see in front of us, is proportional to the inverse of the cube of the thickness. Put another way, a small change in thickness will have a huge effect on the deflection of the part. If we take the accepted industry standards as an example, and we have a simple beam, if we increase the thickness by 20%, so you remember we talked about 10% thick beam, if we increase it to 12%, the deflection reduces to 0.6 of the original deflection for a 10 mil part. If we reduce the thickness of that part by 20%, i.e. from 10% down to 8%, the deflection will almost double. So these are some striking figures that we should try to bear in mind the next time we're moulding and looking at our wall thickness variations. So how else can the thickness of your rotomoulded part affect the quality of the finished product? Well, variation in thickness will have a variation in cooling rate across that part. So what? Well, Unfortunately, polyethylene being a semi-crystalline polymer, it is greatly affected by the cooling rate of the wall during the cooling. The impact that will have on your part will then be one of density. So simply put, the thicker the part, the slower the cooling through that wall, and the thinner the part, the faster the cooling through that wall. So how does the cooling rate then affect the crystallinity, or the crystal distribution, the density of the part? A thicker wall, which cools slower, will give the polymer more time to become ordered and crystalline, and therefore more dense. A thinner wall, which is cooled faster, does not give the polyethylene time to get crystalline and well ordered, and so you will have an amorphous region of the polyethylene. So as you may be able to see in the slide, the upper slower cooling result is a thinner wall, and the faster cooling results in a slightly thicker wall. It's imperceivable, but just showing you for a demonstration here. So that's how you get different densities of material around the part, and those different densities of material will then could then cause dimensional variations and warpage, shrinkage. And if there is anything to be taken from this view of cooling rates and how it affects the dimensional tolerances of your part, it's really complex and oftentimes unpredictable. So as with anything, in order to optimize the wall thickness, we have to first of all find a method to measure the wall thickness of your parts. And historically, there have been two main methods to do that. One is ultrasonic measurement of the wall thickness of your part. And the second, more destructive method is to cut the part up and to use vernier calipers to measure the wall thickness. Obviously, once that is done, the part cannot be used. Worth noting that measuring of parts by this method, cutting and caliper, cannot be used for parts which are perhaps going to be submitted for standard tests at a local laboratory. Ultrasonic has often been used of late within rotomoulding situations. So we are finding more and more ultrasonic customers are moving over to the induction method of monitoring. And this method comparison chart gives you a little idea of why that is the case. So if we start with looking at each method on the left-hand column, we have non-destructive methods, ultrasonic, and K-Metron, the induction thickness testing method. Cut and caliper is obviously destructive. The part is no longer usable after that. Ultrasonic gives you an electronic reading. Cutting and caliper method is very often down to the accuracy with which the user will measure that part. K-Metron also gives you an electronic reading on a display. The next column is titled Material Density Independent. So ultrasonic works by sending an ultrasonic wave through the part. It bounces off the inside surface, comes back to the sensor, and it is that time of flight that the ultrasonic sensor will use to then infer a density or a thickness, I beg your pardon. It is very important to note that the density of the material will affect the thickness read. And we've just heard back a few slides ago how the density of the polyethylene will vary depending on the thickness of the part. K-Metron and cut and caliper They don't care what is in between what the wall is made of. Measure through bubbles. A common issue with ultrasound is once that ultrasonic wave hits a bubble, it disperses and gives back a null reading, an error. Depending on the model and make and model of the ultrasonic unit, it may return a 0 value or it may return a null value. Obviously, cutting and caliper measuring has no effect with bubbles, and the induction method, as with K-Metron, doesn't care what is in between the sensor and the inside surface, unless, of course, it's ferrous. So the K-Metron can only be used to measure non-ferrous parts. So all plastics, GRP, wood, aluminium. So it could even be used to measure the thickness of your aluminium tools. No problem. With ultrasound, you need a coupling gel on the surface, which then needs to be cleaned off. Cutting and caliper, you don't need any coupling gel. With K-Metron, although there's no coupling gel, we do require a magnet to be inserted to the inside surface. This, although may seem like an extra work or something difficult to do, after a short time of using it with the magnet on the string, the operators do not report it being any kind of an issue. The final one is an important one to include, and one we've had a lot of feedback on from our customers to say that one of the main reasons they move from ultrasonic to the induction method with the K-Metron is they have found that the ultrasonic system may give them a reading back, but it will be dependent upon the temperature of the polyethylene, the temperature of the part that they're measuring. So oftentimes molders, as soon as they demold the part, they want to know what the thickness of that part is before they begin again and continue to mold. If you measure the thickness of your rotomolded part just out of the cooling bay and then 24 hours later when it's cooled down, there will be a variation in the measurement that is being displayed on the ultrasonic device. The problem is you don't know if it's wrong. In reality, the ultrasonic device should be calibrated for a particular temperature. Very important. With the K-Metron, it doesn't matter what the temperature of the polyethylene is. It measures the distance between the magnet and the inductive sensor. K-Metron looks like this. On the left, you see it's a handheld unit. On the right, you see it from the side view. There is a curly cable attaching the handheld to the sensor, so it can be separated to measure down deep ribs or around radius. And you've seen on the inside of the part here the magnetic ball. There is a very good and strong magnetic connection between the sensor head and the ball, and we can measure up to 30 millimeters of thickness, 20 millimeters on the vertical, 30 millimeters on the horizontal. And as is shown in this photograph here, we can measure even through solid and foamed parts. So that's one thing the ultrasonic cannot measure through the foamed part, whereas the induction method using K-Metron can measure the thickness of foamed parts. K-Metron also has a radio link, so on pulling of the trigger of the K-Metron, it will transmit by RF signal, by radio frequency signal, to the receiver unit, which will be plugged into the PC. And every time that trigger is pulled, it will send that thickness directly to the K-Metron software and record that on the PC for later exporting to Excel and reporting on as you wish. So, very brief specification table of the K-Metron. There are 3 different magnets that come with the K-Metron. There's the 10 mil cube magnet, and there's the 10 mil spherical magnet, and then there's the 19 mil spherical magnet, all for different thicknesses. The most commonly used is the 10 millimeter spherical magnet, which will measure between 2 millimeters and 20 millimeters. For any distance less than 2 millimeters, the unit can simply be recalibrated. And in fact, supplied with the K-Metron is a set of calibration steps, which will allow the user to calibrate at will and renew that calibration table as needed. The critical window is the time during which the polyethylene powder will lay down inside the moulding. It begins whenever the polyethylene is able to stick to the inside surface of the metal tool, and it will continue until the polyethylene has all melted and stuck to the inside of the tool, which is just above 120, 130 degrees Celsius or thereabouts. So therefore, it's worth bearing in mind that there's only a short window where the rotation speed and the rotation ratios will have an impact on the wall thickness of your part. Once you go into the latter part of the oven and then into the cooling bay, the speed of rotation and the ratios will not be that critical. Therefore, it's important that you have a high enough rotation speed at the correct rotation ratio to ensure an even wall thickness distribution of your material. There are only 2 variables that control the wall thickness of your part. 1, the local mold temperature at that part, and 2, the number of times that part of the mold goes into the powder pool, described here as the powder pool residence time. We have shown here that there are a number of tips and observations that may help you understand better how wall thicknesses are set up within your moulding. So starting at the top right and working our way around clockwise, it's true to say that more even oven temperatures reduce the likelihood of uneven wall thicknesses. Walls will be thicker at the hottest parts of the moulding. Stalling rotation can cause areas of variable temperature, which sometimes can be useful to heat up cold sections of your part. A brief tip is that increasing the rotation speeds, which will increase the number of powder pool passes on each section of the mold, will improve the wall thickness distribution and make it more even. Parts will be thinner at the colder parts of the mold. So for example, in shielded areas or deep ribs or flanges where the heat perhaps from the oven cannot reach adequately, will be colder, and therefore you may get thinner parts. Correctly adjusted rotation ratios will provide the biggest impact to wall thickness uniformity once you have got even heat around the mold. Uneven wall thicknesses will account for more uneven shrinkage and eventually warpage. If you're having problems with your wall thickness variation, then I would recommend processing a part which is a lot thinner than what you would normally process, let's say 2 millimeters thick. And then you will be able to see much more easily the very thin or parts of the moulding, perhaps where there is no polyethylene at all. So if you're having problems, use a smaller shot weight to get a more clear picture of how the wall thickness is varying. Parts will be thinner in places where the geometry inhibits the powder flow. So if the powder is flowing over an internal rib and it's like a waterfall, then the part will be thinner at that area. Slowing down the rotation speeds can help for complex shapes. As I mentioned on the previous slide, powder lays down on the mold somewhere between 85 Celsius and 130 degrees internal air temperature. So that's either side of the melting point of polyethylene. So that's where it all happens. That's where your speed and your rotation ratios are very important. As we've already said, parts will be thinner in those areas that pass through the powder pool less often. So the more powder pool passage you can get, the thicker and more even the part will be at that point. And finally, another tip is if you suspect that uneven heating has been the issue, then you can put an empty mold into the oven for 2 minutes, remove it, and then view it through a small infrared camera, and you'll see where the natural hot spots and cold spots are on your mold. And so that concludes our short presentation on wall thickness measurement and the factors that will affect the wall thickness of your part. Thank you very much for your time and attention. And if we can help you any further, please don't hesitate to contact us at sales@493k.com. Thank you.